Oh, yeah. Honestly, my friend was I was just thinking about it in 10 minutes, but then, they're like, yeah, I'm gonna try to do it in the garage section. Yeah, I'm just going. But I'm not doing it again. We do like really Saturday morning. You're a lot of hours. I already talked to him about it, and he was like, yeah, we're pretty much gonna start going over. We're gonna go over on Thursday, and we're gonna probably tomorrow, and then Tuesday, like, there's some meeting of that. So he's like, luckily you won't be missing this. Okay. I just, there's the angles, he was like, yeah, I'm not supposed to buy for this video. I was off under him, I was like, I know what. Why not?
All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good to hear. All right, so for today, plan for today, we're gonna finish up our lecture notes on upper extremities. So I have a few more examples today, and that's probably what we're gonna spend the most of the time doing. Just talking about different examples, introducing kind of different concepts, and yeah, going from there. All right, so some announcements. Remember the next homework has been posted online, and so it's all about mostly a little bit on kind of the tissue biomechanics stuff that we did last week, but mostly it's kind of static biomechanics problems, kind of like exactly what we're going to do today. So today's lecture is going to be very helpful for the homework. Should give you a lot of good things to look at for that. Okay. All right. Are there any questions I can answer before we get started? Okay. All right, so let's go ahead and pick up where we left off. So actually, first thing I'm going to do, I'm going to scroll back up. So we finished an example kind of last time we were here, but I did kind of want to talk about it a bit more. Okay. So last time we were here, we looked at kind of the first example of a static biomechanical analysis, right? And so we introduced kind of what this was, what we're typically looking for, and and how to go about the calculations, right? So here we have a pretty typical situation of a person holding a weight in his hand with his elbow flexed at a 90-degree angle. And so what we're interested in computing here is, first of all, how much muscle force is required to maintain this position? And two, what are the reaction forces at the joints that result as part of this as well? Okay. Okay, and so of course with this came a lot of assumptions, and so there were assumptions in terms of how many muscles were acting, the moment arm of the muscles, and so on and so forth. Okay, and then we went about solving it, and then the way that we solved this problem was we simply just wrote out the equilibrium equations, and so we summed up all the forces in the x direction, summed up all the forces in the y direction, summed up all the moments about the joint. Okay. And then from that, we were able to get this expression here for the muscle force. Okay. And so I wanted to start here today. So I wanted to talk a bit more about this result. Okay. We started talking a bit about it last time, but basically we were looking at this result and looking at each of the different components in the numerator and denominator, and kind of talk about how those different parameters kind of affect our result. Okay. In particular, the thing that we really focused on was this quantity in the denominator here is Lm. There's Lm here is what we call the muscle moment arm. Okay. And that muscle moment arm is basically the distance between where the muscle attaches, to the bone, to the respective joint. Okay. And so another way that you can think about this is that this is the attachment distance, or the distance from which the muscle attaches from the joint. And so kind of the discussion that we started on Monday was that, this quantity here is in the denominator for the muscle force, right? And so what that basically means is that this quantity is inversely related to the amount of muscle force that's required to maintain this situation, right? And so an inverse relationship basically means that as this quantity goes down, the muscle force goes up, okay? And so intuitively speaking, right? And so, a lot of times we correlate, the magnitude of the force we kind of equate that to the amount of work that's needed, right? And so, we plugged in some typical numbers for this amount, and we found that the muscle moment arms are actually very, very small, right? So typically, muscle moment arms for most of the muscles in your body are going to be quite small. So they're on the order of 1, 2, 3, 4 centimeters. So they attach, in other words, they attach very close to the joint. And when you compare that to the moment arms for a lot of the exterior forces, and so in this case, we have a force that's acting right at the end of the limb, right? You end up with this kind of, it almost seems like a force amplification kind of scenario where, maybe you're only supporting an external weight of 80 newtons, but in order to support that, your muscle has to exert a force of almost 10 times that amount. And that difference is solely just because of the difference in the moment arms, okay? And so you might look at this result and you might think that this is kind of very inefficient, or you might think that your body is kind of working much harder than it needs to when the muscle needs to exert way more effort or way more force than the external force, right? So I wanted to kind of explore that point a bit longer today. And I want to discuss that, there's a very good reason why these muscle moment arms are really small, even though it does result in very high muscle forces. So this first bullet is just kind of a repeat of what I just mentioned. So typically your muscle moment arms, when you measure them in the body, they're typically very small. Okay. And of course, the exact distance varies, depending on the muscle, depending on the joint, depending on where it is in your body. There's also variations between different people. Of course, typically, taller people have larger muscle moment arms, but on average, they're around, maybe 1 to 4 centimeters. Okay. And so because of this, muscles have to exert, pretty high forces in order to support, typical limb movement or to support any kind of external loads. So the fact that muscles have to exert these high forces, it does come with a few consequences, right? Namely that, the more force that a muscle exerts, the more energy that it requires. Okay? And so in particular, if you want a kind of a comparison, the amount of power that a muscle exerts is roughly proportional to the amount of force that it generates squared. Okay. And so the higher amount of force that the muscle has to exert, it requires just a lot more energy. Okay. But that's, I think, pretty intuitive. Kind of the other result that kind of comes from this is that, because muscles always can only apply forces in tension, right? As the muscle exerts more and more force, that causes higher and higher reaction forces at the joints. Okay. Okay. And even though your joints and your bones at the joints, they're designed to take, these amount of forces to some extent, right? Exposing your joints to excessively large forces, especially over a long period of time, that can lead to some health issues as well. Okay? Not really relevant for the upper extremity typically, just because your arms and your shoulders typically don't experience super large forces over a long period of time, but it is going to be relevant in other parts of your body, mostly in your spine. And so, we'll talk about common spinal injuries and kind of how they occur in a couple of weeks. Okay. And so, when I list those out, those may seem like downsides, right? And so, it kind of begs the question of, maybe the human body could have been designed a little bit better to kind of avoid these things. But the reason your muscle moment arms are very small actually has, a very, very important reason. Okay? So the main reason that the muscle moment arms are small is basically to allow your limbs to move quickly, right? So it's your body basically trades off, energy for, for speed. Because the idea is that, with muscle moment arms that are small, when your muscles apply tension, they also contract, right? So we kind of talked about that a little bit under muscle biomechanics. The muscle actually shortens in length whenever it conducts a power stroke, right? So we talked about kind of the protein filaments and them kind of contracting and stuff like that, right? And so with a small moment arm, your muscle only has to contract a relatively small amount to cause a large rotation of your limbs. Okay. And so to illustrate this, let me draw you a picture, okay? Or let me draw you two pictures that kind of illustrate this. Okay? So let's imagine a situation, let's say that we're in medieval times and, we have a castle with a moat in front, right? So typically in those cases, you have a castle and there's a river in front of your castle, right? There's a drawbridge that kind of comes down to let, guests into the castle, right? And so let's say that we have your castle here. Beautiful, ornate Latin architecture castle right there, right? And let's say that we have a river kind of right here. Okay. Okay, so to let people in, typically there is a drawbridge, right? And so if you've never seen a drawbridge before, it's basically a plank that kind of goes over the river like that. Okay. And the way that this bridge is opened and closed, it's kind of almost like a hinge, right? And so typically there's a rope. Okay. A rope that attaches at the end of the drawbridge. There's some kind of pulley right here, right? And there's a couple peasants up here that are just pulling pulling the drawbridge, right? And so to pull the drawbridge up, the peasant here would grab the rope and kind of walk backwards, and that will cause the entire drawbridge to come up like that. Right? Okay. So all these drawbridges are designed basically the same way. So, if you look at the location of where the rope attaches to, it always attaches to the end, right? And if you think about it, the reason for that the reason the rope attaches at the end okay, the reason that that occurs is to minimize the amount of force that's required to pull up the drawbridge. Okay. Because if you draw, let's go ahead and draw a free body diagram here. So if we draw kind of the drawbridge out here, okay. And so the main weight that or the main force that the drawstring has to oppose is the weight of the drawbridge itself. Okay? So this is the weight of the bridge. Okay. And then at the end right here, we have the force of the drawstring, right? So this is the tension of the drawstring. Okay. And of course, the where this rotates around is right here. Okay, so if we do just kind of a very quick analysis here, let's say that we know this angle. So this is the angle of we'll call that theta, right? If we draw a free body diagram, and let's say that we know these lengths, so we'll call this length. We'll say this is the length of the bridge divided by 2. And then let's say that we know the entire length of the bridge L, right? So if we sum up the moments around the joint here, okay, and we use the same convention, the same sign convention that we did last time. So any forces that cause a counterclockwise moment will be positive, and any forces that cause a clockwise moment will be negative, right? And so we have minus T string times L. And since that force vector is an angle there, the only component of that force that's going to cause a rotation is the vertical component. Okay. And so we have to add a sine theta there. Okay. Because if we look at this force vector, right, we break it up into the components. So this vertical component here will be T sine theta, and this horizontal component will be T cosine theta. Okay. T cosine theta is in the direction that points directly at the joint. So, we've already talked about that, any force that points directly at the joint is not going to contribute to the moment, right? And so the only component of that force that's going to contribute is T sine theta, okay? And so we have T sine theta multiplied by the length times sine theta. And then we have the contribution of the moment from the weight of the bridge. And we'll assume that it's we're in equilibrium here, so we'll assume that it's 0. Yeah, question? Yes, thank you. Getting ahead of myself there. Okay, so let's go ahead and let's solve this for T. Okay, so we have a common factor of L here on both sides, right? And so we have T string is equal to the weight of the bridge divided by 2 sine theta. All right. So that's a relatively low amount, right? And so this is only, the weight, basically half the weight of the bridge with an added factor of sine theta, right? And so, if your bridge is not that heavy, maybe you only require, 2 or 3 peasants to pull up your bridge, right? Let's compare that to a situation where the drawstring kind of is closer to the joint. So this second situation here is going to be closer to, it's going to be closer to how your muscles are mostly designed. Okay. Let's draw a bridge. Okay. Just like before, we have the weight of the bridge coming down. And so we'll say that distance there is L over 2. Okay. But this time, let's say that our drawstring is attached almost right at the base, right? Okay. And we have an angle theta there. And so let's say that this distance is L over 8. Okay. So it's only 1/8 down the distance of the bridge. Okay. We can do the same thing. So let's go ahead and sum the moments around the joint, right? And so we'll get the exact same equation. The only difference is that the moment arm for the drawstring is going to be much lower. Okay? So you have minus T string multiplied by L over 8 sine theta, okay, plus W bridge times L over 2 equal to 0. Okay. Okay, so once again, we'll solve for the tension. We'll solve for T. So we're going to cancel out L on both sides. I need to multiply both sides by 8 in order to get rid of that 1/8 on the bottom, and then divide by sine theta. Okay. And so what we get from this is T string is equal to W bridge times 4, all divided by sine theta. Okay. So obviously, much bigger than our previous result. Okay. So this one, you probably need, compared to the previous one, you need 8 times as many peasants to raise the bridge. And so if you needed 2 peasants before, you need 16 now, and peasants are, I'm assuming, are kind of expensive, and so that seems like it's not ideal, right? But if you look at the design of these 2 bridges, and if you were to ask me, which one would be more advantageous in the event of like a zombie apocalypse, right? And so let's say that you have zombies invading your castle, and you need to draw the bridge up quickly. This design is actually going to be better, right? It may require more work, but on the flip side, you're able to bring the drawbridge up much more quickly. Right? Let's see why that is. Okay, so if you look at this drawbridge, in order to kind of fully come up right here, right? And so in order to pull the drawbridge up, you can kind of imagine that this bridge or this plank here has to make a quarter rotation, right? So I have to go from basically 9 o'clock to 12 o'clock, right? If the string is attached at the end of the drawbridge, that means the amount of distance that the string has to travel is basically the same as this arc right here, right? It's a little bit less, I know, just because the string kind of makes a straight path to the end, but we can approximate as kind of a quarter rotation around the circle. Okay? So if we compute that, if we compute distance to close, okay, the distance to closing in this case would be a quarter of a circumference, right? And so circumference of a circle is 2 pi times the radius, but in this case, the radius of our bridge is L, okay? And a quarter of this would be divided by 4. Okay. Okay. So that's the amount of distance that the bridge or the rope has to be pulled in order to fully close the bridge. Okay. Let's compare that to the second situation. Let's compare that to how your muscles are designed, right? Once again, this bridge has to make a full rotation, but instead of attaching at the end of the bridge here, we're attaching much closer to the joint, right? And so once again, we have to make a quarter rotation, right? But the radius of that rotation is much smaller in this case, right? And so once again, a quarter rotation, we're going to multiply pi over 2 multiplied by the radius of that circle. But we know that the radius of the circle now is L over 8 as opposed to L, right? And so the amount of distance that we have to travel to close the bridge in this case is pi L over 16. Okay. And that makes a really big difference, right? And so if your peasants can only pull the string at a fixed speed, right? Bridge number 2 is going to close much faster than bridge number 1, right? Okay. And usually that's the case too. And in fact, your muscles work exactly the same way, right? Okay. And so muscles also can only contract at a fixed speed. Or maybe the more accurate way to put it is that there's a limit to how quickly your muscles can contract, right? And it all depends on how quickly that your muscles can execute that power stroke, that the protein filaments can kind of slide past each other, right? There's a limit to how quickly your muscles can contract, right? It's not that you can kind of infinitely keep increasing the muscle speed, right? And so in a situation like this, where the amount of contraction, the speed of contraction is fixed, right? In order to maximize the amount of speed that you can that your muscles can contract and your limbs can move, that attachment distance, that moment arm, has to be small. And generally speaking, evolutionarily, I try to make up a word, in terms of evolution, generally having, faster moving limbs, and, it's that basically allows you to run faster, allows you to hit things harder, allows you to react faster to things. That's generally more advantageous than minimizing the amount of work. Just because if you find, if our ancestors ever found themselves in a situation, they had to run away from a bear, or they have to like strike a tree to get, wood or something like that, being able to rotate your limbs faster is a lot more advantageous. Okay. So that's the main reason why, your muscles attach, your muscle attachment angles, or excuse me, your muscle moment arms are very small, is to ensure that you can rotate your limbs, quickly and respond quickly to certain situations. Okay. All right. Any questions on this? Okay. All right. So that was a big detour from a relatively simple result. So let's do another example. Okay. So in that last example that we did, we did a very simplified case where we only considered one muscle, right? You do have certain joints in your body where there's only one muscle primarily working at that joint. But for the most part, most joints are acted on by multiple muscles at the same time. Okay. So let's actually, kind of repeat the same example. So let's consider a situation where you're supporting a weight in your hand. But let's bring some other muscles into it as well. Okay. Okay. Let's consider the elbow joint once again, but we'll consider multiple muscles in this case. Okay. All right. So let me go ahead and draw the elbow joint again, so that we have our upper arm here. We have our elbow joint. we have our lower arm, and we have our hand. Okay. Just like before, we're going to have some kind of weight or some kind of box that the person's holding. Okay. So that's going to be held at the end of the lower arm. But now we're going to consider multiple muscles, right? So I'm going to go ahead and draw in those muscles here. Okay. And it's going to get a little bit busy, but I'll kind of try my best. Okay, so let's start with the muscle that we considered last time, the biceps brachii. Okay. Okay. So that's one muscle. The next muscle that comes down is the brachialis muscle. So let me go ahead and I'll use another color for that. Okay. So that's the brachialis muscle there in purple. And then the third muscle that we're going to consider is the brachioradialis. Looks kind of something like that. Okay. So we have three muscles to consider in this case. Okay. So just like before, what we're interested in is we want to do a static analysis here. And so the things that we're going to compute. Okay. Let's compute the magnitudes of all of the muscle forces involved. Okay. And then also, just like the previous problem, let's compute the reaction forces at the elbow joint. Okay. So let's list all of our assumptions here. All right, so first thing we're going to assume, and this is going to be typically true for most of the problems, all of the geometric parameters and lengths and stuff will be given to you. Okay. So that includes the lengths of all the limbs as well as the moment arms for each of the muscles, as well as their attachment angles as well. Another thing that we're going to assume that we're going to know, and this information is relatively new, is that we're going to assume that we know the cross-sectional areas of all the muscles involved as well. Question, yes.
Do we assume that cross sections are relatively constant in the muscles?
They're not constant, but what's going to be important in this case is the relative cross-sectional areas.
Okay.
And so typically when someone mentions the cross-section of your muscle, it's where the cross-section is the greatest. And so you measure that one. Yeah, so we're going to assume that we've measured each of these muscles at their greatest kind of cross-sectional area, and then that's known to us. All right. Any questions on just the setup of the problem? Okay. All right. So let's get to solving this. And so before we start the solution process, let's count the number of unknowns that we have. Right? Okay. So we have three muscles that we need to solve for their forces for. Okay, so that's three muscle forces. Okay. And then we have two reaction forces at the elbow. Okay, so we have the reaction force in the X direction and the reaction force in the Y direction. Okay. So in total, we need to solve for 5 unknowns in this problem. Okay. And so that kind of seems to imply that we need at least 5 equations to solve for this. Okay. So let's see how many equations that we can get from the equilibrium equations. Okay. All right, so to next step is let's go ahead and draw our free body diagram. Let me go ahead and draw the lower arm here. Let me draw it big just to leave myself a lot of space. Okay. Okay. So first, let's add all of the known quantities here. So we have the weight of the object at the end. Okay. Just like we did in the last example, we're going to assume that the weight of the lower arm itself is going to contribute to weight. Okay. So we have W arm that's acting right in the middle. Okay. Let's assume that we know the total length of the arm here. Okay, so this length here is L. And then we're going to assume that the weight of the arm is going to act right at the midpoint. So it's going to act at L/2. Okay. Let's draw in our muscle forces now. Okay. So let's start with the biceps brachii force. And actually, let me make a legend up here just to make it a bit easier. Okay. So biceps brachii, we'll call that FM1. Okay. Just like the last example, we're going to assume that it points directly upwards. Okay. And it has a muscle attachment or muscle moment arm, we'll call it L1, little L1, okay? All right, so the next muscle that we have is the brachialis muscle, and so we'll call that FM2. Okay. And then we also know it's a moment arm L2. Okay. And so unfortunately, things do get a bit messy because we do have 3 muscles attaching very close to each other. Okay. But we're going to assume that the brachialis attaches a little bit further away from the joint than FM1. Okay. So in purple here, we have FM2. Okay. And this distance is L2. A lot of parameters in a small space. So I'm trying to arrange them so that it's kind of you can kind of see all of them. Okay. All right, and then the last muscle that we have there is the brachioradialis. Okay. And so we'll call that FM3, and then its attachment distance is L3. Okay. And so I'm going to exaggerate this a little bit. I'm going to pull it out here just so you can see it. Okay. And then this distance here is L3. Okay. All right. So one new thing about this problem, although not new to today, we kind of discussed it a little bit with the drawbridge, is that the brachialis muscle and the brachioradialis muscle, they're attaching at a specific angle, right? They're not just perpendicular to the limb itself. And so we have an angle θ2. So θ2 is going to be the angle at which the brachialis muscle attaches. Okay. And then the brachioradialis muscle, we're going to assume that it attaches at an angle θ3. All right, so a lot of parameters here. And of course, you can plug in typical values for these, these are things you can kind of easily look up. But once again, we're going to solve these things, or we're going to solve this problem primarily with variables, just so that we can look at the result and kind of, see what conclusions and what patterns that we can draw from. Okay. Okay. Any questions on the free body diagram here? Okay. All right, so let's get started with our equilibrium equations. All right, so let's sum the forces in the x direction. Oh, I forgot two very, very important things. Sorry. The other forces that we need to consider here are the joint reaction forces, right? So we have at the elbow joint on the left-hand side here, we have the reaction force in the x direction, so we'll call that Jx. Okay. And then we have our reaction force in the y direction. I'm going to point it straight up, Jy. Okay. I apologize, I forgot about this. Okay. Now let's get back to the equilibrium equations. So let's sum all the forces in the x direction first. Okay. So in the x direction, we actually have three forces here. And so the first force that we have in the x direction is Jx. Okay. Right. We have three vertical forces here. So we have Fm1, the weight of the arm, and the weight of the object. All three of those forces are perfectly vertical, so they're not going to contribute anything to the x force summation. Okay. But we do actually have contributions from Fm2 and Fm3. So let's go ahead and write those in. Okay. So Fm2 is kind of pointing diagonally up to the left. And so we want to take the horizontal component of that force. And so that's going to be Fm2 multiplied by cosine θ2. Okay. And then we want the horizontal component of Fm3. So we're going to do a minus Fm3 cosine θ3. Okay. And this is all equal to 0. Okay, so let's do the same thing in the y direction. Okay, so we're going to sum up all the forces in the y direction. So we're going to start with Jy. Okay. In this figure here, we've pointed Jy upwards, and so in the equations we have a positive Jy. Remember, it doesn't really matter all that much which directions that you choose with the joint reaction forces. As long as you stay consistent in all of your equations, then it's perfectly fine. Okay. Okay, so we have Jy pointing upwards. We have the three muscle forces. All those are pointing upwards, or at least one of their components do. Okay. So we have plus Fm1. Okay, so Fm1 is pointed vertically upwards, and so we don't need any sine or cosine here. We have plus Fm2. We need the vertical component, so that's going to be Fm2 sine of θ2. And then same thing for Fm3. So Fm3 sine θ3. All right, and then we have the weights, our two weights here. So we have the weight of the arm and the weight of the object, W. Okay. And all of that's equal to 0. All right, so our y summation here is quite a bit longer than before, just because we have more forces to account for here. Okay. All right, and so finally, the last thing we have to do is we have to sum the moments. Okay, so we need our moment equation. And remember, you can choose where you sum the moments around, but in 99% of the cases, you want to sum it around the joint. Okay. So this is going to be the sum of the moments around the elbow itself. Okay. And remember, what that does is that, when you sum the moments around the joint, the two joint reaction forces are not going to show up in the moment equation, right? So it kind of saves you a bit of work. Okay. So let's go ahead and add these in. So first we have FM1 multiplied by L1. Okay. So we take the component of the force that's perpendicular to the limb itself, multiplied by its distance, or the moment arm. Okay, so that's FM1 L1. We use a positive sign because FM1 here is producing a counterclockwise moment around the point. Okay. Next, we have the contribution from FM2. So we have FM2. Okay. Multiplied by L2, the moment arm. But since the FM2 is acting at an angle, we need to add the sign there as well. Okay. Right. Because if you look at the horizontal component of that horizontal component points directly at the joint. So it's not going to contribute anything to the moment. Okay. And we're going to have the same thing from FM3. So plus FM3 times L3 sine of theta 2. All positive. All right, and then finally, we have the contribution of the moments from our two weights. So we have the weight of the arm. Okay. In this case, the weight of the arm points vertically downwards, and so it's already kind of perpendicular to the line of action to the joint itself. Okay, so we have minus W arm multiplied by L over 2. Okay. And then we have the weight of the object, W, multiplied by its length, L, and all that's equal to 0. Okay. All right. Any questions on the equilibrium equations that we got here? Okay, cool. All right, so these are our typical 3 equations, right? So you're going to get these 3 equations in every static problem. Okay? But we have a problem at this point, right? So we have our 3 equations, but we already have established that we need 5 equations to solve this system, right? So we have 3 muscle forces and the 2 joint reaction forces. And so as it is, this set of equations here is not going to be enough to solve this system. Okay. And so there's a term we have a term for this in statics. So we say that this system is statically indeterminate. Okay. All right. And so it may seem like we have an issue here, but typically and hopefully you guys remember from your statics class too that statically indeterminate systems are actually good, right? So whenever you have a statically indeterminate system, what that basically means is that you have some redundancy, right? You have some extra forces, you have some extra supports in the system, more than is needed to actually stabilize and satisfy the system statically. you know, and as engineers, we know that redundancy is good, right? You don't want to rely on just a single actuator or a single engine or a single, you know, you don't want to rely on one single part to do a very important job, right? And so your body is kind of designed the same way. And so if you remember, you know, when we talked about, you know, all the different muscles in your body, you know, there's way more muscles in your body that you really need to do most of your actions. But the reason you have so many is because, you know, you need some redundancy in the system, you know, to make sure that, you know, if a muscle goes down or if it gets injured, or maybe, you know, there's some issues with your nervous system, you can't, you know, innervate a certain muscle, you know, you're still able to kind of do what you need to do. Okay. So redundancy is good. So the fact that, you know, we have this problem means that your body is generally well designed, and we're only considering 3 muscles in this case, right? But it does make it difficult for us to solve a problem like this because we're not able to get a result from the 3 equations that we have. Okay? And so in order to move forward, we need a bit more information, and we need a bit more assumptions. Okay? All right. So I'm gonna discuss, you know, 2 different approaches. You know, one that, you know, we're not quite ready to apply yet. You know, we're going to talk about that technique kind of later on. I do want to mention it now just because it's kind of very relevant to the problem that we're doing. And then the second strategy is the one that we're actually going to use for this problem. Okay. So the first assumption really isn't an assumption. There's a lot of really well documented evidence of your body actually doing this. And which is the fact that, you know, when you have a redundant system, you have redundant muscle forces acting on a particular joint, the way that your body distributes the load between those muscles is to minimize the amount of power or the amount of energy that's required to execute the action. Right? Okay. So, you know, energy is a fairly finite resource, right? And so, you know, the main way that we intake energy into our bodies is by eating food, right? But we can only eat so much at a certain time. And so, you know, if your body's able to minimize the amount of energy and power that's required, you know, whatever food that you do consume or the calories that you have can go a lot further. Okay. And, you know, there's a lot of evidence that your body kind of automatically does this. It's fascinating in a way, actually, because, you know, this kind of, you know, strategy here is kind of hardwired into your nervous system. So your body always innervates muscles in a certain ratio that kind of makes sure that, you know, it minimizes the energy required. Okay. Because, you know, if you remember from earlier today, one way that you can kind of estimate the amount of power that's required to for a muscle to generate tension is to take the amount of muscle force and you square it. Okay. And so because of that, because the power is kind of has the square relationship, you know, it's pretty advantageous to have one muscle, you know, take in all the load. Okay. Okay. And so you may look at it, you may look at this and say that, yeah, you know, that makes sense. You know, so should we just divide the amount of force that's required and divide it by 3? Unfortunately, it's not that simple because there's other factors in terms of, you know, the different moment arms for the different muscles that also plays a role. And so the muscles with a larger moment arm will naturally just, you know, have to exert less force. And so there's going to be more load placed on those muscles, right? The attachment angle that we're going to discuss a bit later, that also plays a factor as well. And there's also kind of metabolic differences as well between the different muscles in terms of, their relative size, the direction of their fibers, and so on. So it's actually quite a complicated problem to actually solve this in practice. Okay? And so to actually solve this power minimization problem here, and I know that there's a couple people in my 454 class, so maybe your neurons might have been activated when I said minimize, but the real way to kind of solve this problem is to use a technique called optimization. So optimization, just in a nutshell, is a mathematical technique that's kind of designed to solve systems with more more unknowns than there are equations. Okay. So we're not going to do that yet, and so this is a topic later in the class. Once we're kind of near the end. But I want you to know that this is kind of the the gold standard of how this problem is usually solved. So. If for biomechanics that are kind of analyzing a motion, they take in all the muscles that contribute to that motion, and then they solve an optimization problem to see how that load is distributed. Okay, so but we're not going to do that right now. That's a little bit too out of a little bit beyond kind of what we can accomplish right now. So the second way that we can solve this problem is to make an assumption based on the cross-sectional area of the muscles. Okay. So basically the assumption is that muscles with the larger cross-sectional area are going to be able to produce more force than the ones that don't, or the ones that have less. Okay. So basically, the bigger the muscle is, the more force that it can generate, right? So kind of like it's almost kind of like your eye test, right? And generally, this is actually a pretty good assumption because if you look at kind of how a muscle is designed, right? A larger cross-sectional area means that muscle has more muscle fibers that are acting in parallel. Right? And if you have more fibers that are packed in parallel, that means you have more kind of protein filaments that are executing a power stroke, and so that's going to generate more force. Okay, so it's a pretty rudimentary assumption, but it's actually real life it actually follows this pretty well. Okay, of course the difficulty in using this assumption here is actually measuring the cross-sectional area of the muscle itself. I kind of just mentioned it at the beginning and kind of brushed it off as if it's trivial, but it's really kind of not. And so if you want to really measure the cross-sectional area of a muscle, you kind of need an MRI or something to do that because all the muscles are kind of interwoven and kind of overlap each other. And so it's kind of hard to go up to someone and measure the exact cross-section of their biceps brachii when there's a few other muscles that are going in there as well. Right. So of course, to solve this problem, we're working with some information that typically is not readily available, but it's what we're going to use to solve this problem. Okay. Okay, so mathematically, the one way that we can kind of put this assumption into practice is to say that the amount of force that the muscle can generate is proportional to its cross-sectional area. Okay. Okay. So basically what we're saying is that the product of one muscle, so let's say that we're looking at the biceps brachii muscle. So the product of the muscle force multiplied by its cross-sectional area is some constant. Okay. Okay. And that constant is the same as the product of the muscle force and the cross-section area for each of the muscles. So this is equal to FM2, A2, and FM3, A3. Okay. So we can use this fact to set up some proportionality relationships to give us some additional equations that will solve our system. Okay. And so if we kind of combine these equations together and we kind of set it up in a convenient way, you know, one such equation would be, say, the ratio of FM1 divided by FM2 is equal to A1 over A2. Okay. Oh, excuse me. I set up these proportionality equations, but it's not the product of these two that are constant. It's their division that's constant. There we go. Yeah. I knew something wasn't right. Okay. All right. And then similarly, we can set up another situation. So let's say that we make a relationship between muscle 1 and muscle 3. Okay. So you have FM1 divided by FM3 is equal to A1 over A3. Okay. Okay. You can form a relationship between, you know, muscle 2 and muscle 3, but that equation is actually redundant. Okay. So this gives us the other two equations that we need. Okay. So this is equation 4, equation 5. Okay. And so we can use these equations to solve our system. All right. Any questions on any of this? Okay. All right. So from here on out, you know, it's a lot of algebra to solve for the system. I'm going to solve for one of the muscle forces for you, and then from there you can kind of plug in and kind of do the rest. Okay. So let's solve the system for FM1. Okay. So this is the biceps brachii force. Okay, so the way we're going to do this is let's start with the moment equation, because we already know that the moment equation doesn't have any of the joint reaction forces. So let me go ahead and write that down again. So we have the sum of the moments around the elbow joint. We have FM1 L1 plus FM2 L2 sine of theta 2 okay, minus W arm times L over 2 minus WL, all equal to 0. Okay. All right, so this equation here has three unknowns, and so our three unknowns are the three muscle forces. But let's use our proportionality relationship to plug in for FM2 and FM3. Okay. Okay. So let's solve equation 4 for FM2. And so from this equation, we're going to move FM2 to the other side of the equation. We're going to move the ratio of the areas to the other side. Okay. We get FM2 is equal to okay. FM2 is equal to FM1 multiplied by A2 over A1 And then we can solve equation 5 for FM3. Okay. And so we have FM3 is equal to FM1 times A3 over A1. Okay. All right. So now let's take these two results and plug it into our moment equation. And what that will do is that will give us one single equation to solve for FM1. Okay. Okay. So let's go ahead and accomplish that. So we have FM1 L1 plus FM1. I'm plugging in for FM2 here, times A2 over A1 times L2 sine of theta 2 plus FM1 times A3 over A1 L3 sine of theta 3. Okay. Times W arm times L over 2. Minus WL, all equal to 0. All right. So it's a lot of terms here, but everything, we only have one more unknown. And so from here, it's just algebra to kind of solve for that FM1. Okay. So first thing I'm gonna do, I'm gonna move the two weights to the other side of the equation. So W arm and W. Okay, let's move that to the other side because they don't contain FM1. And then for everything else, I'm gonna factor out FM1 from that expression. Okay. All right, so on the left-hand side, we have FM1 times quantity L1 plus A2 over A1 L2 sine of theta 2 plus A3 over A1 L3 sine of theta 3. Okay. This is equal to W arm times L over 2 plus W times L. Okay. All right, and then from here we just divide by everything in the square brackets. Okay. And so our final result, FM1 is equal to W arm times L over 2 plus W times L divided by L1 plus A2 over A1 L2 sine theta 2 plus A3 divided by A1 L3 sine of theta 3. All right. Any questions on this result here? Okay. All right. So I do have a couple more examples, but we don't have time for it today. And so the last thing I want to discuss today actually is these sine terms down here. Okay. All right. So from this example, we have another result here that computes a muscle force. And so let's kind of do the same thing where we kind of analyze this in terms of what's in the numerator, what's in the denominator. Okay. So there's a lot more that we can talk about. And so, obviously the ratio of the cross-sectional areas are there. But one thing I do want to mention here is these sine terms. Okay. Okay, so we have sine of an angle, right? And so that angle is not insignificant. Okay. So theta 2 and theta 3 here, these are known as the attachment angles. Okay. And so when your muscle attaches to one of your bones, right? So your muscle attaches to your tendon attaches to the bone, right? That tendon is always going to attach to the bone at a certain angle, right? So that's what these angles are. Every muscle in your body has a different attachment angle, right? In our previous example, we assumed that the attachment angle was 90 degrees, so it kind of wasn't a factor. But when that angle is different, then you have it factors into the result here. Okay. Typically speaking, attachment angles is typically an acute angle. So this is something that ranges from anywhere between, well, it can almost never be zero, but maybe something like around 0 to up to 90 degrees. Okay. And so if you look at our result there, you can see that, it's the way that the attachment angles appear in our result is that we take the sine of that angle, right? And so if we know that these attachment angles range between 0 and 90, and we know that the way that they appear in our result is as a sine, that tells us a bit of, how that attachment angle affects our result. Okay. And so I'm going to make kind of the same argument that I made with the moment arm, right? And so entries or ways that the that sine of that angle will be maximized, that's going to reduce the amount of muscle force that's required. Okay. Okay. And so if you think about sine of an angle, right, what angles are going to maximize sine? So the sine of an angle itself ranges from 0 to 1, depending on the angle, if we're restricting ourselves to just between 0 and 90, right? And so if the angle is close to 90, that's going to maximize sine of theta. Whereas angles that are closer to 0, right? The worst possible case is that if you have an attachment angle of 0, then sine of theta is going to be 0, right? Okay. And so generally, generally speaking, when you have muscles that attach at an angle that's close to 90 degrees, that's going to minimize the amount of force that's required from your muscles to, do certain tasks. But if your attachment angle is 0, and basically an attachment angle of 0 means that the muscle basically acts, almost parallel to the bone that it attaches to, then those muscles are going to need to work pretty hard in order to generate a moment. Okay. But unlike moment arm, I know we spent the majority of the time today or the early class today talking about how it's advantageous to have a short moment arm. There really isn't an advantageous, an advantage of having a small attachment angle other than, it makes your joints a bit more stable. Okay. So attachment angle really kind of just depends on just the geometry of your body, the geometry in which the muscles attach. The attachment angle does actually vary. So in different poses of your body, your attachment angle can change. And, you know, that kind of explains why certain motions are easier in certain positions than others. Okay, but we'll talk about that more next time. We'll start our discussion on Monday. Any final questions before we wrap it up for today? Yeah.
So this is more of a conceptual question. So with the assumption that the larger cross-sectional area of the muscle will produce more force output. When you think about like world-class athletes like me and Olympics, right? We have dudes that weigh like 60 kilos.
Mhm.
They're pretty skinny, but they're able to clean and jerk, so like more than half, or more than double their body weight, right?
Yes.
So
Mhm.
how does that, you know?
Yeah, so there it's, you know, just kind of simplifying in terms of just cross-sectional areas, more power. I mean, of course, that simplifies it a lot. You know, for those athletes, you know, they probably have a lot of fibers, but they're probably just more densely packed. Whereas, you know, other people, you know, may have bigger muscles, but the fibers may be more spread out. Depends on your fat content as well, because fat can kind of go in between the muscle fibers and make it seem bigger, but it really doesn't produce a lot of force. And so those athletes probably have incredibly dense muscles that can produce a lot of force with a small amount of space. Yeah. All right, any other questions? Okay, that's all we got time for today. So I hope you guys have a good weekend. And I will see you guys on Monday.
Thank you, Dr. Mann.
Yep, have a good weekend, guys. See ya.